Most scientific experiments are designed to uncover a new detail about how the physical world works. But every so often, an experiment produces a result so strange, it forces us to question the actual nature of reality itself. The setup for the double-slit experiment looks remarkably basic. You only need three components: a source that fires electrons, a physical barrier with two extremely narrow vertical slits cut into it, and a sensitive detection screen sitting in the back to record exactly where those electrons land. For a long time, the rules of physics were straightforward. We understood electrons as solid matter, tiny physical projectiles. And if you fire tiny physical projectiles at a wall with two holes in it, you expect them to behave like microscopic bullets. If we look at this schematic, the classical prediction is clear. Each solid electron should pass cleanly through either the left slit or the right slit. Traveling in straight lines, they would hit the back screen and eventually build up into two distinct vertical bands. But that is not what the screen recorded. Instead of two solid bands, this updated model shows the electrons creating an interference pattern. They landed in multiple alternating stripes of bright and dark spots, a pattern you only get when overlapping waves ripple through both slits, collide, and interfere with one another. Electrons have a measurable mass. They are solid fragments of matter. Yet as they traveled through the vacuum, they somehow stopped behaving like physical objects and started acting like immaterial waves. Faced with this contradiction, scientists looked for a practical explanation. The most obvious answer was that the electrons were simply crowded. If you fire a massive stream of particles, they might be ricocheting off one another mid-flight, scattering like billiard balls to create those alternating stripes. To test this, they carefully tweaked the experiment. They turned the electron source down to its absolute minimum setting, releasing exactly one electron at a time. The particle would travel entirely alone, hit the screen, and only then would the next one fire. At first, the screen just showed random isolated impacts, one solitary dot. A few seconds later, another dot somewhere else. The process dragged on as hundreds, then thousands of individual impacts slowly accumulated. This mathematical probability visualization illustrates the paradox. As dots built up, the exact same multi-band interference pattern appeared. A single electron was traveling forward as a hazy cloud of probability, moving through both the left and right slits simultaneously. The math forced a conclusion that defied common sense. An individual, indivisible piece of matter was somehow splitting apart, passing through two separate locations simultaneously, and then crashing into itself before hitting the screen. Scientists are not comfortable with indivisible matter splitting in two. They needed to see exactly what this single, isolated electron was doing at the precise moment it reached the barrier. To catch the particle in the act, they upgraded the apparatus. They lowered highly sensitive path detectors directly into the vacuum chamber, locking them into position right beside the double slits. With the monitoring equipment active, they fired the solitary electrons again. This time, the sensors would definitively record which specific slit each individual particle traveled through. In this split-screen comparison, we see the dramatic result. The detectors successfully logged the paths, but the moment measurements were taken, the interference pattern vanished. The electrons stopped acting like waves, behaving like physical bullets stacking into two simple vertical bands. Nothing physical about the barrier had changed. The only difference was that a new piece of equipment was recording data. The mere act of observing the electron forced it to choose a single path, stripping away its wave-like behavior entirely. This raised a deeply unsettling question. Was the electron physically bumping into the magnetic field of the new detector, or was it reacting to the fact that we were simply watching it? Physicists devised a variation called the delayed choice experiment to rule out physical interference. They set up complex optical paths and synchronized electronics to stall the measurement process. Instead of monitoring the slits directly, they let the electron pass through the barrier unobserved. They configured the system so the path data would only be extracted while the particle was already in midair, flying toward the final screen. By that point, the electron had already cleared the slits. If it was acting like a wave, it should have already split. Yet when the delayed measurement was captured, the result was exactly the same. Two solid bands appeared on the screen. Manipulating time and physical distance did not trick the particle. Even when the decision to observe was made at the very last microsecond, the electrons still collapsed into a solid physical state. The exact timing of the measurement was completely irrelevant. This left one final extreme test. If the physical equipment didn't matter, and the timing didn't matter, scientists needed to see if the outcome depended purely on the existence of the information itself. This became known as the quantum eraser experiment. This logic flowchart maps the final procedure. The detectors were left on to record exactly which slit the electron took. But before anyone or anything could read that path data, the information was diverted, scrambled, and destroyed. The system took the measurement, then discarded the results. The moment that data was permanently erased, the multi-band wave pattern retroactively reappeared on the main detection screen. It wasn't the physical sensors that collapsed the wave, and it wasn't the timing of the machinery. The structure of reality shifted based purely on whether or not the path information was available to be known. In the quantum world, the observer and the observed are permanently and inextricably linked.